In this lesson we're going to take a look inside the logic gate, and this will lead to the introduction of the transistor, specifically the MOSFET or field effect transistor. And where we're going to start is by recalling the basic gates that we have looked at so far in studying an introduction to digital systems. So we have an AND gate, OR gate, and NOT gate. And we have not considered at all how you might construct one of these. The only thing that we've really looked at is what we've called the static discipline, which defines the voltage levels at the input and the output of the gate. So let's take, for instance, the inverter. So we have, now we're going to go back and actually look at voltages. So we have ignored voltages. We've just talked about high and low, 0 and 1, basically these lumped values, when we were looking at Boolean algebra and implementing a logic gate. But now we're going to have to consider the fact that in any real digital circuit there are actually voltages. So here is the DC transfer characteristic of an inverter. And the idea is that if the input is low, then the output is going to be high, right? And vice versa. Let me label these here. We'll assume 5 volts for our levels. And so we might have a transfer characteristic. Ideally, it would be up here. Let's say this is 2.5 volts. I'm going to get it here. Okay, 2.5 volts. This would be the ideal DC characteristic of an inverter. In other words, here, if VI is less than 2.5 volts, then we'd have VO is equal to 5 volts. And if VI is greater than 2.5 volts, then VO is low. Now recall we had defined the static discipline, which meant that, and we had a VO high level, we had a VO low, and when we had drawn it, let me draw it one last, the way that we had actually described it or depicted it initially was like this. We had the input side over here, we had the output side here, maybe we called this the sender, and here the receiver. So we defined VO high and VO low, and over here we had VI high and VI low, and remember we had these, drew this line, and the difference between VO high and VI high was the noise margin high, was the upper noise margin, and labeled noise margin NMH. And similarly for the lower limits, we have noise margin low was VI low minus VO low. So in other words, any logic circuit that complies with the static discipline is going to agree to put out for its output signals to comply with VO high or VO low. So logic low will always be less than or equal to VO low, and any logic high output will always be greater than or equal to VO high. And then any inputs to that logic gate will have to comply with the VI high and VI low. So if you give it a voltage that's below but up to VI low, then it will interpret that as a low, and if you give it a voltage that's greater than or equal to VI high, it must interpret that as a high. So let's assume that we do that here on this logic gate, and we're going to redraw this DC output transfer characteristic with those labels. I'm going to use some colors here. Okay, so we'll have VI high, VI low, and VI high. Now this here, this is the input, right? The horizontal axis is input, or if you will, you could call it the receiver side. And the vertical axis is the output or sender. Okay, but in this context, we're talking about logic gates, so it's really input and output. So let me draw some dashed lines here, indicating these thresholds. Okay, and so our inverter, although it generally has this shape of going from high down to low as we increase in our input voltage, we don't know exactly how it makes that transfer, that travel for a particular inverter gate. However, if we're told that that inverter gate satisfies a particular static discipline, then we know the region in which it must, or that transfer characteristic must lie. So let me try to depict that here. I'm going to put some cross hatching here. Let me extend this. For the inverter, what we must comply with is, I'll explain this in a second. So our transfer characteristic must lie in this hatched area. Meaning that if it does, then by the time that VI low, or by the time the input voltage reaches VI low, the output must be equal or greater to VO high. So if we were to have a transfer characteristic that came around this corner just like that, it would barely meet our static discipline. If it came around this corner down here, just barely, that would be at the threshold of meeting our characteristic or our static discipline. Okay, so this is okay, and this red one is okay. Let me show you a transfer characteristic that would not be okay. So if for some reason our transfer characteristic came down and crossed over here like this is not okay because of that region right there. It goes out of the hatched area, meaning that we are below, see, if VI is less than VI low, then VO must be greater than or equal to VO high. Okay, so it must be for an inverter. For an inverter satisfying this static discipline. And in this case, it's not. Okay, so this is the extent to which we have looked at anything electrical regarding a logic gate. We have simply defined some voltage thresholds on the input and on the output side to which that gate must comply if it is said to satisfy a particular static discipline. And if you're going to combine logic gates together to implement logic functions that maybe you've minimized, then each of the gates used in that logical circuit must comply with the same static discipline. Otherwise, you're going to get faulty logic traveling through the circuit because there'll be different voltage references. A high from one gate coming out of one gate will not be interpreted as a high in another gate unless they're satisfying the same static discipline. So now what we want to look at is to think a little more on how do we actually implement a one of these gates. We're going to start with what we have really in hand so far, and then we're going to have to introduce the transistor as an element that we will need in order to be able to implement these logic gates. So let's look at what I'll call diode-resistor logic. So this is a first look at trying to implement some logic gates. So using only resistors, diodes, and we'll use we can use some voltages, like a voltage source, an OR and NOT gates. Okay, we'll recall for the OR gate, if we have an input, and I'm going to put VA here. Well, let's start with A and B input, and our output is A or B. Then this is the truth table. If we convert this to voltages, okay, so now we're going to look at VA, VB, and VF. And let's assume that we're going to assume 5 volts for VIH. Actually, what we're going to assume for the moment is, yeah, we'll assume VO high is equal to 5 volts and VO low equal to 0 volts. Then we would have 0 volts. 0 volts will give us 0 volts. 0 volts and 5 volts would give us 5 volts, and so forth. 5 volts and 5 volts would give us 5 volts. Now right away when you see this, you realize, okay, we can't be dealing with the linear circuit, because if we were, and we had 5 volts at the output when just VA was 5 volts, then you'd say, wait a minute, this VF must be 10 volts in this case. But clearly, I already told you we're going to use diodes, so we will not have a linear circuit, and so there is a way that we can have 5 volts at the output when both inputs are 5 volts, and still have 5 volts at the output when just one of those inputs is 5 volts. Now let's look at how we might implement this OR gate with just diodes and resistors. Consider this circuit here. So I'm drawing VA and VB. This implies that there's a voltage source tied, between that node and ground, having a voltage VA and a voltage VB. Okay, but I won't show that. And let's consider the case where, what if these two voltages, I'm going to redraw it a little bit differently here, just to help you conceive of what's going on. So if we have 5 volts and 0 volts, and this here is VF. Okay, and we call this DA and DB. These are ideal diodes, so when they're on they have 0 volts. Now look at that circuit. We have a single loop, right? Nothing's connected to VF, and I know I've left off the resistor for just a moment, but what I want to focus on is how are these diodes turning on or off. So if the source on the right, VB, is 0, and the source on the left is VA, and we have those diodes, you see how they're oriented facing each other, right? So the first thing to realize is that because they're pointing in the opposite direction, you're never going to be able to get any current flowing from one source to the other source, in other words, through that loop. This current, the current flowing around here, this will always be 0, regardless of VA-VB, regardless of VA and VB values. So you try any one, what'll change is which diode is blocking. So if we reverse the voltages on VA and VB such that VB was 5 and VA was 0, we would now have DA, diode A, would be blocking, as opposed to diode B, which is blocking currently when VA is 5 volts. Okay, so the next question is to think of what would be the voltage VF for those different scenarios. So in this case that we have drawn here, if VA is 5 volts, then DA is on and dB is off. Right? In other words, it's certainly dB that is blocking. It's supporting the 5 volts that's made up of VA minus VB. So because DA is on, we have VF is equal to 0. VF is equal to 5 in this case. If we were to reverse this, and we actually now had VB equal to 5 volts and VA 0, then it would be diode B that would be on, but again, VF would be 5 volts. And then lastly, if both VA and VB would be 5 volts, then there's 0 volts across both diodes. And so the voltage VF then is also 5 volts. So you see that? If VA is 5 volts, then VF is 5 volts. If VB is 5 volts, then VF is 5 volts. And if they're both 5 volts, then VF is 5 volts. And the only time that they're 0 is when both of the inputs are 0 volts. Now you might say, well, why do you have this resistor in here, this R? Because I didn't show it to the right. Well, for any practical diode, you need a little bit of current to flow through it to make sure that it's on. And so this resistance is, not critical, just, let's say, just less than infinity ohms. Okay, just some little ohms, some small amount of conductivity. So this is a diode circuit. Now it works. We can use this in some contexts, but it does not. It doesn't have a very useful transfer characteristic. Let me show you what the problem here. The output voltage VF can be expressed this way. It's going to be equal to the maximum of VA and VB. Okay, so here we have if VA is equal to, VA is equal to 0, we're going to sweep VB. If VB is equal to 0 volts, and we sweep VA, then we see the same thing. So the problem is this. What you really should have, okay, if we define a VO high and a VO low, a VI high and a VI, oops, did that backwards, and this is OR gate with, we'll say VB is equal to 0, and so we'll sweep VA here. What we should have is something that falls in these regions here. Actually, let me redraw this one last time, because those VI high and VI low should be more closely together. In other words, they have to fall inside here. They got to be inside the VO low, VO high, VI low, VI high, and so we need to be in this region here. Oh, wait a minute. I'm sorry. This is not inverting. So in this case, what we want, it needs to be in this region here, like that. And we don't. It doesn't do that at all, right? What it does is it does like that. Okay, so although roughly speaking, I mean, it does implement the V output is the maximum of the two inputs. So in other words, one could be 0 and the other input will drive the output. There is no transition. All right, it's just this gradual growing of VF as a function of VA. And what we really want is something that's going to have a clear transition around some pretty narrow voltage band, VI low to VI high, and we're not seeing that here. So that's a problem, but in some cases we can still use diode logic. Let me show you one example just to maybe help clarify, because I claim that we can make an OR gate with 2 diodes and a resistor, and then now I'm saying they're really not very useful. Well, they're not useful when you think of a static discipline. You can't implement any static discipline of any real functionality for the purpose of creating, logic gates that you can then build expressions with. However, you could do something like this. Suppose you want an LED to come on. So LED should come on whenever we have two doors, whenever door 1 or door A or door B is opened. Imagine we have a door here that is going to swing open like this. This is A, and then B door opens, and inside here, I'm not going to draw it so well, but we would have, let's say that this is a symbol for a push button switch. Okay, so this is a normally closed tactile or momentary switch, but when you apply a force, there's a stem right here, that's the mechanical end of the button. So when nothing's pressed on it, there's a spring that holds it up in contact with the two terminals of the switch, such that current can flow through that switch from one terminal to the other. But when there's an external mechanical force applied to the stem of that momentary switch, the metal contact, which is this bar down here, that's metal contact, moves away from the two contact points, and there's an open circuit. So that's the idea here. If we have a door that has one of these switches, then when the door is closed, the switch would be actually pressed, would be open, because it would be depressed. So we'd have two of these switches. So this will be switch A, and this will be switch B, and we're going to just use our diodes. Over here, we will tie them both up to 5-volt supply, and then what we'll do, we'll have a resistor, but really we're going to put in an LED to ground. The doors will be closed, and so these switches will be open because the door is closed. But when either door A opens or door B opens, or both doors open, then current will flow from the 5 volts through the resistor, and the LED will turn on. So this would be useful if you wanted to have a little indicator that said if the light's on, then either door A or B is open. So that's a good use of, appropriate use of a diode OR-ing circuit. But we're not doing combinational logic, and we're not going to build Boolean expressions with lots of gates this way.